Welcome back to a video that looks a little bit different. We're not in my car just talking about whatever wildlife we've seen. We're sitting at a table, we've got lights. We're a little bit more prepared today. And talking about being a bit more prepared, I've actually done a bit of research and written down some of the talking points that I want to use throughout this video today. My goal is to make a simplified, short and sweet, very condensed and basic understanding of data or digital storage. Because I realized up until this point, I've never really discussed or explained most of the things that I'm doing. I've just kind of left it up to someone to either have the understanding of what it is or to look it up on their own, and that's not entirely fair. I also don't think that it's fair to just say, I need more space and expect that to be a coherent and explainable answer. I think it's a much better answer if you can dive down into the nitty-gritty on the how and the why so you understand where it's coming from, and then that answer makes a lot more sense. So the goal is to cover these three main questions. What is data and how it works? How does data pertain to digital photography? And what is the scale that affects me / what am I doing in the future about my data? So the first thing, what does data stand for? D-A-T-A. Nothing. It's not an acronym. But it should be, so I made my own. Digitally archiving technological anteaters. And those are the small anteaters that live inside your computer and keep everything clean and running smoothly with those long tongues of theirs. Data is kind of an all-encompassing term. We use it to describe a lot of things, really, but it could be an email, a digital document that's legally binding and addresses exactly how much cheese I'm allowed to eat in one serving. It could be a photograph or a video in our cases. So how does a computer do this? And also why? The why is because data can be safely stored and then accessed at a later point in time. And the how is a little bit more complicated, but basically how a computer works, or the way they did back in the day, by using binary code, a sequences of zeros and ones that it is able to convert into processes and know what to do at what point in time. Computers kind of still use binary code today. A lot of, when you get right down to it, it does go to that, but there's also something called machine code. It's a whole other topic that I don't fully understand, so I can't really explain it. But what you would see as programming today is using a specific language that would be more readable to humans and not so much computers, that then gets converted into binary code so that the computer knows what you're talking about. So how does data pertain to digital photography? Well, in order to understand that, you really have to understand how a camera works. And I think it's a little bit easier to wrap your head around if you take a step back and talk about a film camera. A film camera works by taking a light-sensitive piece of material, the film, and exposing it to a source of light, like the sun. The sunlight comes in and hits that film, and it exposes whatever it can see in the scene through its field of vision. If there's a dark tree, you're taking a landscape photo, you'll get lots of light in from the sky and not so much on where the tree is, and then you get the shape of the tree, and you get to see that. All of that information is stored on the film until it's developed later in a darkroom. A digital camera works very similarly, except instead of film, it is an electronic sensor, and that sensor is made up of pixels. A pixel stands for picture element, and there are a lot of them. Modern cameras are measured in megapixels, so the individual pixels on the sensors are then counted up. A megapixel is technically a unit of graphic resolution equivalent to 1 million pixels. So each megapixel is a million little tiny individual pixels. And those pixels are not just on a sensor, but they're on the screens that you're viewing this on, a lot of devices. Now, if we pretend that a camera records black and white photos in binary code, each pixel would only need one of two digits, a 0 or a 1 for black and white. But that's not really how it works. What you need are 4 possible combinations to get a little bit of gray in there. What they call a 2-bit image is this combination. You have 0, 0 for black, 0, 1 for dark gray, 1, 0 for light gray, and 1, 1 for white. Those 4 combinations to each pixel make up a black and white image, because you do need a little bit more separation between that. So the camera would take the picture, and each individual pixel would record one of those 4 numbers, all of that grouped together, and it makes the image. So now, each pixel has a job to do. Shutter goes up, and during the exposure, each pixel needs to record one of those 4 numbers in correlation to how much light it's getting in the scene. But what if we want color? Well, that actually is a huge topic that probably could be its whole video on itself, and to be fair, I only have a basic understanding of it. So to keep things simple and easy, we're just going to simplify it to each color, besides the white, gets its own channel. And you only need to make up 3 channels, a red, a green, and a blue, RGB. Each one of those, for this process, is going to get 8 possible options, 8 shades of red or green or blue, or white and black. That, in total, makes up a 24-bit pixel. A 24-bit pixel is what they use to create 8-bit color. Here's the thing about 8-bit color, as great as it is, it was developed by IBM in 1987, and things have come a little way since that. This camera is a Canon 5D Mark II. It came out in October of 2005. This camera takes photos in 14-bit color. What that means is that because of the math for each shade, it could have over 16,000 shades per channel of those 4 channels that we just talked about, which means a possible 4 trillion different shades, individual shades of color. And it records that data for each pixel. This sensor in this camera has a resolution of 5,616 by 3,744, meaning that it will come out to be 21 million pixels, or 21 megapixels. That's where things start to get big, right? So let's try to create an example to keep things imaginable, because I, for one, when large numbers start coming up with no frame of reference to attach them to, my eyes just kind of glaze over. So let's pretend that we just sat down at our computer, opened up a Word document, and typed in a single character. That single character we're going to say is 1 byte. It's not actually, it's a little bit more complicated than that on the size of things. Just pretend along with me so that this makes sense. Now, we've typed in our single byte character. What if we wanted to fill that page? We just hold down the button and fill the entire page with a character. For our example, let's say that that page can fit 1,024 characters. Again, not actually how many characters fit on a page, but bear with me. We now have one page with 1,024 characters on it. That is a kilobyte, because it is 1,000 of a byte. Why is it 1,024 and not 1,000 even? Because of math. Technology doubles. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. It's also how most things are counted up in the digital storage that you may already be familiar with. So now we have our piece of paper. Let's say we printed that piece of paper out with our 1,024 characters. That is a kilobyte. What if we printed that page 1,024 times? Put that into a book that now has 1,024 pages. That would actually just be slightly smaller than the Lord of the Rings trilogy, which is something that I looked up earlier when I was trying to find a book that was exactly 1,024 pages for this example and could not. Our book is now a megabyte in size, because we have 1,024 pages inside of this book, with each containing 1,024 characters on it. Megabyte is much more common, and you probably know about it. Let's jump back to the camera. This camera takes still images that average out to be around 25 megabytes. It's not exactly, that's just my own finding on it. It has a range, and it depends on how much it actually gets onto the image. If you're taking a picture of a landscape and there's a beautiful sky but not a lot of clouds in it, and you've got a lot of grass on the ground and you're getting that, the grass is going to contain a lot more data because there's a lot more there for it to take in with the different shapes and colors, whereas the sky kind of gets compressed into one thing because it's all a very similar color. But every time I press this button, it captures a 25 megabyte image. That's 25 of our books that we just talked about every time I press the button. It's a lot of data, but we're not even halfway done yet. Now, what if we took that book that we had and we made 1,024 of them? And then we put all of those into a library. It's a small library. I imagine you could fit 1,000 books into a room, although I've never tried. But let's say that that is our library. Our library is now the size of a gigabyte. Again, another common term that most people are probably already familiar with, but you might not have ever imagined it at this scale as to exactly what it is. This is where the metaphor starts to fall apart a little bit, because you can't really stack or combine libraries that much. Just imagine, if you will, there's a very long street, and along this long street are 1,024 libraries in a row, each library containing 1,024 books that has 1,024 pages with 1,024 characters per page, all the way up through there. The collection of libraries is now a terabyte, or 1 trillion bytes. This is a 2 terabyte hard drive. This is essentially what I use as a memory card inside of this 4K camera whenever I go out and shoot with it. This holds double all of the data we've talked to up until this point. 2,048 libraries would fit inside this. And I regularly fill them up. You see, this camera over here has a slightly smaller sensor than this other one, but it shoots at a 4K resolution, and I shoot 60 frames per second. That means every second that I'm shooting, it's gathering almost 12 million pixels of information. Times 60, because it's 60 frames in a second. It's 716 million pixels worth of data every second. What that equals out to be is that for a 2 terabyte hard drive, I get about 91 minutes of recording time at the highest possible quality. Now I can shoot at a lower quality and get more time out of that, but then the footage doesn't come out looking quite as crisp and nice, which is what I'm going for. What that means is that this camera, every second of recording time, I'm capturing 384 megabytes of data, which, if we go back to our previous analogy, is 384,000 pages, or 384 libraries every second that camera is recording. Now I don't keep all the footage that I shoot, which is good because there's a lot of it. I only keep the things that I consider to be good. If it's not in focus, if it's over or underexposed, if there's not actually wildlife in the shot, I typically don't keep those. I delete them, which is good because those hard drives are essentially just memory cards. Put them in the camera, take them out, shoot, fill them up, bring them home, offload them, empty them, take them out, and start all over again. That means that my computer at home, I need a lot of space. I have about 20 terabytes worth of space currently, and you'd think that would be a lot. That would be one of those hard drives 10 times over. But in reality, it's not that much because I have multiple hard drives. I have 5 terabytes that I take out as a memory card. If I were to keep every single thing that I shoot, I would fill up my 20 terabytes in 4 days of shooting. That doesn't really work. Storage is not that cheap. So we hit an impasse. Which really brings us to the main point of why I'm making this video and especially the next video, where I'll be expanding my storage space. I've kind of hit a capacity, and I've had to start deleting footage that I would normally consider good and want to hang on to. The reason I hang on to them is because I'm still very much learning of this process, but raw footage can always be edited to look better, and I'm still learning how to edit. I want to be able to hold on to that. Even in the 1.5 years that I've been doing this, I've made huge strides from the first videos I ever edited, and I've learned so many more techniques that I can do. Techniques that don't really work if you use processed footage, which is how the editing process works. You kind of bake it in with all of the changes that you want to make. I can't take that and work some of them back. It doesn't look quite as good. It's much better to keep your raw footage and be able to use that for future edits, which is why I want to hang on to particular clips. Unfortunately, we recently had a bit of a downturn here where I deleted some footage that I really wanted to keep. I did not mean to delete it. I have to do kind of a juggling act between when the data comes in from my memory card hard drives before it goes on to the permanent storage drives. And I thought I had backed something up that it turned out I did not. And I deleted it by accident. And it was sage grouse footage, which I'm really proud of and really excited, and I lost an entire hard drive's worth, which means that I lost a whole camera angle from one of the days that I went out. It had some really good stuff on it, and I'm a bit sad. Hopefully this gives you a little bit more understanding into the how and why I need as much storage space as I need for the data that I'm creating, because of how big it is. And also a little bit of an appreciation for the sheer scale of what it is that I'm doing and how big these files are that we work with. It's massive and quite honestly intriguing when you see something that is of that size. Even if it's just numbers on a screen, seeing that larger number is kind of exciting. And as I said before, I think it's a lot more interesting to understand exactly through the thought process as to how and understand the question instead of just giving the answer, I need more space.